Okay, welcome everyone. So first, are there any questions from last class? That I know you had time to go and read again the material, search on the internet. Your head is full with questions that you want to ask right now. Okay. So last class we were looking at layout of production systems in a very just the generalities, okay, and why they look the way they look, in particular for offshore systems. Okay, we saw, for example, the need to have two lines, that you need to have two production lines or production and test line. When we don't have that in place, we have some complications, especially with subsea. Remember, the first thing is, if we have subsea wells, the tree doesn't go all the way to the platform. Then we have a problem that we are going to discuss later, that is called flow assurance. Okay. That basically we want to that there will be no interruption, or the fluid will be produced from the reservoir to the facilities with no interruption. Okay, no problem. And there are many problems that kind of jeopardize the continuous flow from the reservoir to the platform. And one of them that we discussed is wax, but we are going to discuss some more. And in that particular case, to have these two parallel lines and perform pigging or be able to flow something through the loop is extremely important. When you don't have it, there are some workarounds, like to use a multi-phase meter and also to use a subsea pig launcher, but these is a very expensive operation. So you have to mobilize a vessel, you have to connect it in place, it will take time, it will take resources, and imagine if it's something that you have to do every month, for example. It's something that the OPEX is going to increase dramatically for that particular field. Okay. Okay, so but the topic for today is offshore structures. For oil and gas production. And if you think about it, the offshore structure is like the central point. We really have something very, or like that represents the field, right? That is the subsurface. That's all the accumulation, the characteristics of the oil, the pressure that we have, how much oil and how much gas we have, what kind of pressure support we have to the reservoir. But then we have some other central point, which is the destination. We are going to send all of that to some place where we are going to process it. And that's usually, in offshore developments, is an offshore structure. And I want to exclude here from this discussion for example, drilling vessels. Okay, so let's put here, we are not going to discuss drilling vessels. We are not going to discuss drilling vessels or ships. We are not going to discuss vessels to lay equipment or pipes. We are not going to discuss tankers. We are not going to discuss supply vessels. Okay. We are going to focus mainly on what you say for oil and gas production. Okay, where we have, and we will see right away, we have a series of components that are usually common in this offshore structure. Okay, one of them is the drilling, what we call the drilling package. Okay, and this is, okay, all of these that I'm going to mention here are like all the possible things that an offshore structure could have. Okay, but it doesn't necessarily have to have all of them. And we will see right away there are some limitations. Which type of offshore structure can have one of these things that I'm going to list here. Okay, so the drilling package, and these are facilities for well drilling and intervention. And that means the drilling tower, you need to have the BOP, you need to be able to circulate mud, so you need the mud pumping and processing system. You need cementing system. This we call usually the mud pumping and processing, we call it the mud package. You need the storage deck for tubulars. All the drilling strings that you're going to use, you have to have them stored someplace, and also if you're going to for casing, tubing, so you need some place to store the tubulars, and you need also the drilling risers. So see, that occupies a bunch of space in the platform. So if we want that our platform to have the option to drill in the future or to perform intervention, that's going really to occupy, first it's going to weight quite a lot, and that's going to occupy a big space. Then other things that you have, some facilities for light well intervention. Not invention, but intervention. Okay. Wireline, coil tubing. If we need to make some intervention in the well, but we don't have to take out the tubing, okay, we don't have to make a full intervention. We can do it through the Christmas tree. Then processing facilities, the central part and the destination of the reservoir fluids, processing facilities. Okay, and here we have the gas processing train, and we are going to talk a bit about that later. But gas processing train, oil processing train, or really oil, what we call last class oil, or the separation train. Okay. Water processing train, polishing unit. Okay. Then what else do we need? If we are performing gas injection, we need also some gas injection system. Okay, that we need basically some compressor trains, and we need also the valves. You need also the pipes to send that that gas to the reservoir. Then we need also maybe gas compression system for pipeline transport. Remember that the gas we have to have, okay, there are no floating LNG, so we have to have a pipe. If we are producing gas, we have to have a pipe and send it to shore or send it to some place where it's going to be used. So we need to have to increase the energy of that gas so it will go from the platform to every place to its final destination. So that's the gas compression system. Then we have the gas lift system. Okay, that's an artificial lift method where you inject gas at the base of the tubing. You in light, you reduce the density, and then you reduce the pressure drop through the tubing. Okay, so if you have a gas lift system, you also have to have compressor trains, okay, pipes, valves, etc. Let's see what else. Okay, the water, if you're performing water injection in the reservoir, you also need the water injection system. Okay, and usually this is done with seawater. So you have to treat the seawater and prepare it to inject. So seawater treatment. Okay, so you have to remove all of these organisms, all of these biological organisms, treatment and pumping. Then you might have also the living quarters, okay, where people and engineers and operators are spending time. You have a gym, you have a nice cafeteria with nice food, you have the cooking place. Okay, you have then the heli deck, or this what we call or the access point. Usually in the North Sea, we come by helicopter. There are some other places in Brazil where you can come also by boat. Okay, and you are towed into the lifted into the platform. You need also power generation, and this is usually done by gas turbines. That, like you know probably, is a combination of a compressor plus a turbine. And plus also, so you have compressor, you have a burning chamber, a burner, and then you have a turbine. And some now we are, for example, Goliath, it doesn't have a power generation, but it brings the power from shore. So that's a trend that they are trying to implement in the North Sea, that we don't generate power locally, but we bring the power from shore. And the reason is because when you do power generation in platform, the efficiency is very low. Okay? When you do it onshore, the unit can be much bigger, and then the efficiency can be higher. Let's see, flare system. Okay, if there is, you're doing you need to close the system for some reason, you need to do maintenance, you need also to evacuate the hydrocarbons in the system, evacuate the gas, so you send it to the flare. If you have an emergency, you send it to the flare. So where I burn gas, okay, when needed. Okay, only in a emergency situation. And the flare is usually that when you see the offshore structure, that you see a very long thing or a structure sticking out of the platform. That's where you have the flare, and that's to be very far away, so if you start burning all that hydrocarbon, it won't reach the platform, it won't affect the platform. Then we have utilities, and in the utilities we have hydraulic, power fluid, okay, pneumatic, sorry, not pneumatic, compressed air, compressed air we use, for example, for the seals of the rotating machinery. Drinking water, air conditioned, ventilation, and heating system. Okay. What else? Okay, we have a place where we have, I showed you on Tuesday, we have a place, if we have dry trees, then we need a place where to put all of those trees. So that was, we call a well bay, okay, where we have all the Christmas trees. And also we have, on top of it, we have the drilling tower, usually, we have a drilling tower. Well bay, we also have the production manifolds. Okay. We have the metering. We have sometimes, and we are going to look that we have storage, oil storage. Okay, not gas, oil storage. And I'm going to continue here on the side. There are not many things to go. Facilities for oil offloading. Okay, usually the offloading to a tanker of the oil, you don't do it in the platform, but you do it on a floating structure, a buoy that is just next to it, far away from the platform. So you have to send a system that will pump the fluid from the platform to the buoy. And then you have a control system, the monitoring system, then you have the system to recover production chemicals. Okay. And here we have, for example, we inject corrosion inhibitors, we inject wax inhibitors, we might inject hydrate inhibitors, we might inject scale inhibitors, all kind of inhibitors. So corrosion, we have scale, we have wax, and we are going to talk, when we talk about flow assurance, we are going to talk a bit about that. Corrosion, scale, wax, then you have some, it might be that the oil and the water, they tend to form an emulsion. Okay, they tend to form a very uniform phase when you shake them very hard, and they don't want to separate. So maybe you want to add an emulsifier that will help that these two phases they separate. Because if really they don't separate, at the end of your separator you have oil with a lot of gas, and that you cannot sell, you cannot send it to the tanker. Okay, the water you want to throw away from the overboard, and the oil you want to send in the tanker. The emulsifier, what else? Hydrate inhibitor. Okay. And then we might have some minor things, but one thing that maybe is important, we might have a repair workshop. Okay? When we have to dismantle something and we have to do a very simple inspection, or very simple, so you need to have a place where to make that. So quite a lot of things. Okay, it's almost like a small city. So let's see how can we make a very rough classification of offshore structures. Okay, and we have first that we have bottom supported. Okay, and here we have two categories. We have fixed and we have compliant. Fixed we have two, and we are going to show just right away a picture, a jacket. Maybe we can pull it right away. And so this bottom supported is that they are somehow fixed, and most of the weight is lying down on the seabed. Okay, it's transferred to the seabed. So in bottom supported, you know, it's not nice at all, the handwriting, but I apologize. So most of the weight and the loads and all the loads that are generated by the sea, they are transferred to the soil. Okay, most of the loads are transferred to the seabed. Okay, are transferred to the soil. Okay, and here you have jacket, you have gravity based structures that they are really fixed. Okay, you can say that the motion is small enough that you can say that is fixed. You have nothing that is really 100% fixed, that is not going to move. You will have all the time some vibration, but these vibrations are small enough that you can say it's fixed. Okay, and then in compliant you have a particular type, is kind of a jacket that has some movement, and that's because it's very, very long. Okay, so it's called compliant tower. Okay, let me pull then just some pictures. Okay, the jacket, maybe you have seen before. That size is okay. Can everyone see the screen? Yeah. Okay. A jacket, difficult to transport, not so difficult to assemble, but it's a hassle to transport and to put it in place. Is not is with its weight itself. It is not enough to keep it in place. Okay, with its weight, because it has the weight of the metal structure and the weight of what comes on top, and that's not enough. So you have really to drive some piles that they nail it into place. Okay, so after you put it in location, you try to hammer some anchors all the way to the soil, and that's how you reach this transfer of forces from the structure to the soil, to the surrounding soil. And of course here is very important, first, if your soil is stable, it's not going to crumble with time, it's not going to, let's say that you're producing the reservoir, it might be that you have some compaction because you're taking out material, and then it might go down, and that might affect the stability of the structure. So that's some things that have to be taken into account with jackets. Okay, then you have the Norwegian proud gravity-based structures, concrete platforms. Okay, so that's gravity-based structures. Okay, that they are made. I didn't bring a real picture. Okay, but they are made in the. Norway had a very strong concrete industry, so they decided to use all of this knowledge and expertise to build these big structures. Okay, and the thing is that they stand by themselves, by their own weight, but they have a system that it's called suction anchor. Okay, where it's an empty chamber where you have the soil, for example, here is anchor, and then you drain out the air and you make some kind of suction cup effect. Okay, and that's how also you keep it in place. That helps on top of the weight to keep it in place. Okay, suction anchor. And if you see all of, okay, so we need, you say, we know these legs, okay, they are to support the structure, but why do we need all of these domes? And these are for storage, okay, to store part of the production that I have. I store it there, and we will, talk why do we need storage and when we don't need storage a bit later. Okay, so these two, very rigid, they have some movement, but really not something that you can say that is going to harm or is going to cause significant movement. And then you have compliant tower, which is a variation. This is really only used in the Gulf of Mexico. Compliant tower, that is, if you can think about it, is like a very long jacket. And the trick here is that this compliant tower, you allow some movement. At the end, you allow some rotation in this joint. There is going to be some rotation and some movement. So you have really, if you're standing on top, you will see some deviation, some meters, and that's going to affect also all the equipment you have in the platform. Okay, but still you have mainly, most of the load is transferred to the soil. Also you have that you can put some supports, some wires, and to fix it and to try to make it more rigid. Okay, you can put some mooring lines that they are trying to keep it in place. And this is called Buoyant compliant Buoyant tower. Okay, and that's more or less everything we have on the bottom supported structures. Okay, any question? No? Yes.
There are three types. Like, is there any specification to use one of them?
Yeah, we are going to talk now how we select them. Okay, just after I'm going to present first what we have, and then how do we select which one, how to determine which one to choose. Okay, then we go to another category, and I'm going to bring the block down. Okay. Okay, and the other category is what we call floating structures. Okay, And in floating structures, we have floating structures are those that are just kept up mainly by buoyancy. Okay, they are kept afloat. Okay, or they are keeping above the sea level by buoyancy. Okay, this famous principle that I think was Archimedes. He was having a a bath in his bathtub, and then he put some things on his side, and he saw that they floated. Okay, this old story. And also they have movement. Okay, they have movement. Okay, that is determined by the waves, by the wind, and by the current. And we are going to talk also in this class about that. Let's see. They have movement. So this is, so let's put it here, something else. Bottom supported. We have, I forgot to put some more comments. Wait. Okay, and have reduced movement in the vertical and horizontal direction. Okay, if you think vertical, I'm referring to this direction, and horizontal, I'm referring to that direction. So they have really limited movement. Now this one, they have movement in the vertical and horizontal direction. Okay, and they also, so the buoyancy you control, the buoyancy is controlled with the ballast tank. Ballast tanks allow me to control the buoyancy. Okay, how much, if I have a ship, okay, and I have here the sea level, in the ship usually have some compartments that I can fill with water to bring it up or down. So these are the ballast tanks. I can regulate, put some more water inside, then it will sink, I will remove the water, and it will go up. So you need some ballast pumps that bring the water overboard when you need to change the. And that, of course, if you think, if I'm storing something in these structures, some liquids, some oil, then I have to be careful to have the right balance between ballast and storage. Okay, keep that in mind. Sometimes these operations can be very, very difficult. How to know how much oil, then how much water, to keep it in the same place. Some structures, if I don't do the ballast correctly, it can be a catastrophe. Okay, to control buoyancy. Okay, and there is one more thing, that they are typically moored. Okay, that means that I have some can be a chain, just a metal chain, can be also some lines that are made out of not plastic, but yeah, this, how do you call it, polyester, all of these are plastic materials.
Polymer.
Yeah, some polymer, but it has another name. I forgot now, but let's see. Did I put here? Okay, but they are typically moored with steel chains. Okay, steel chains. Or can be also with pre-tension. That's called composite lines. Okay, and steel chains, if you have, for example, let's say that here you have the vessel, okay, and here you have the seabed. The steel, usually they go kind of in a catenary shape. Okay, that's called a catenary. Okay, while the pre-tension, you have that they follow, they might have some catenary initially, some catenary shape, but then they start being straight. Okay, and here you have the anchor point. and here you have someplace the anchor point. Okay. For that, if you are using this particular type, this is called taut mooring. This is called catenary mooring. If you are using catenary mooring, you use these very big steel chains. If you are using taut mooring, it has to be tensioned, okay? And to have this elasticity, you need to have some composite material, okay? Okay, so now finally we go to what goes inside the box. We have two things, okay? We have neutrally, let me make some space, or I don't have. Okay, so inside floating structures we have naturally buoyant. Okay, and inside here we have Fpso, which is just like a boat, like a ship. Okay, probably you have seen it. We have Sevan Fpso, a specialty type of Fpso. Remember, Fpso stands for?
Floating.
Floating is one. Production.
Storage.
And?
Offloading.
Offloading, okay. Floating. Production. Storage. And offloading. Okay. Sevan Fpso, then I have a semi-sub, that there can be many variations of the semi-sub, and we are not going to talk about all of them. Then we have a spar. Okay, these are all the natural buoyant. And we also have, so let's maybe show some pictures before. Okay, so these are, so remember, they are floating, they are chained or they are attached to the seabed by two types of mooring, okay, and depending on every structure has a different kind of mooring. And the catenary, the difference is that the loads are usually very close to the horizontal direction. The pulling, when this tries to move to the left, you feel some pulling, but it's on the horizontal direction, on this point, on the support point. But on taut mooring, the force on this support point, it goes very much inclined. Okay? So let's put some live to our slides. So that's a Fpso, just a boat, just a ship. Okay? And here you can see the lines, the mooring lines. Then I think we have some sketch. So that's called Fpso. Okay, or we call it also ship Fpso. Then we have the Sevan type Fpso. Okay, that is similar to that floating structure, but it's just round. And I'm going to just try to explain very briefly why. So in this arrangement, if the sea is very changing direction, if the waves are changing direction, you usually, for example, let's imagine that here you have a lot of waves that are coming on this direction. The ship is going to try to bend, and you have, if they are very big, the waves, you have the danger that it will just turn over. Okay, so if that happens, you are in a very, like, let's say, harsh sea, you try to orient the vessel in front of, so it will be oriented in the same direction as the wave, or in the same direction as the wind. Okay, so for that reason, you have that all of these mooring lines, they are just in one point, and that point is all the time fixed, and the boat is rotating. So you have a joint that is called a swivel. Is that more or less understandable or not? So let's put, okay, here we have our boat. Let's see if I try to make it nice. Okay, and here comes the wind. Okay, so you have one central structure where everything, all the lines from the whales, all the mooring lines is attached to that point. But that point stays all the time fixed. But the boat is able to rotate around this joint. So this is called a swivel. Okay? Yeah. And this is a very complicated mechanism because if you see here I have a pipe and here I have another pipe, and to be able to transfer production I have to find a smart way to do it. So this is really where you pay all your bucks in an FPSO, it's in the swivel. Okay? What this guy said in Sevan is say, really, why do we need the rest of the ship? Okay, let's put everything, let's just take out that part, like the middle of a cake, and that will be my FPSO. The problems, the space, you have less space. Storage, to put things on top, etc. Yeah? So that's called a swivel and is fixed. Usually it's fixed, while the rest of the boat can rotate and orient depending on where the sea comes. The sea, okay. Then we have what we mentioned then was the semi-sub. Okay, that looks like that, and you have the sea. Of course, these parts are not visible; they are just below, and that's where you have the ballast. Okay, and there are different types with different number of legs. You might have they have something now called octosub that have 8 legs. You might have like a square joining all of them. There are different designs, but that's what I call here semi-submersible. Yeah. And you see here, that's the drilling tower that I was telling you about. And you have a crane, and I'm not sure, the flare might be this one here. Okay. So that's Njord. And you see in this case we have a drilling tower and we have a bunch of lines that these are all the production lines coming from every well coming from subsea. Okay. Then we go to spar. Okay, the spar looks something like this. So FPSO, semi-sub, jacket, and gravity-based structure are very common in the North Sea, like very common in offshore Norway. Then spar is not common. It's mostly used in the. That's a spar. Okay. Okay, and it's so long because then when you make it shallow, it's more prone to the movements of the sea and of the currents and everything. When you make it very, very long, it tends to be a bit more stable. Okay? SPAR stands for, or they are also called deep hull structures. Let's see, I didn't put it here, but the hull is for example, if you have the sea, the hull is all the part that is below the sea line. Okay, so in this case, the hull, if you have the surface here, has a big hole exposed to the sea. Okay, to the current. So that's why sometimes they call it deep hull structures. And again, we have like in the semi-sub, we have different variations, and they have different names. And don't be confused. Sometimes they don't call them spar, but they call them deep hull structures. Okay. Well, you have different types. You have everything closed, open, like like almost like a jacket, but really is the same principle. Okay.
Excuse me.
Yes.
Why is there like a circular thing on the hull?
Anybody knows? We have some guys bright guys from mechanical engineering, right? They study that in their. No. When you have circular structure, if you see it from the top, okay, when some current is impinging, okay, into the vessel, you have, if it will be ideal, the fluid will just go like this, okay, and continue. But really, we know nature is not so easy, and that's not what it happens. What it happens is that you have some turbulences, it goes and breaks loose before that middle point. Okay, but this phenomena is also not steady, but sometimes you have that it oscillates up and down. This point where it detaches, so this is the detachment point. Okay, it goes up and down. Okay, it oscillates. So you get at the end some wake. You get some wake. Okay, that starts to affect, and you have vibration on the structure, and it induces quite a lot of vibration on the spar. Okay, so you make these strange things that he was saying, these helical things, just to break this wake effect. Okay, this is called vortex shedding. Okay, this is called vortex shedding. Okay, and our friends from marine department, from mechanical engineering, they have a lot of fun simulating these things. Okay, yeah, clear, more or less. This is like fluid dynamics in 30 seconds. So yes, so that's par. Okay, and then we have one last thing that we didn't mention. Okay, so those are the naturally buoyant structures. Okay, and just keep in mind now for the future that all of them have a lot of movement, but spar, because if it's a deep hole, it doesn't have the motion, is not so much like in the others. Okay, nowadays the first spar will be installed in, I think, 2019 in Osta Hanstein, okay, Norway. The first spar in Norway, very deep water. And then we have another category called positive buoyant. Okay, and this is called TLP, Tension Leg Platform. An intention leg platform, let me see if I have, I think I have a figure, or I should have. Okay, it's buoyant, it's floating, okay, but the thing is that you attach it to the seabed and then you pull it down, okay, or better said, you first fix it in place and then you remove the ballast, and it will want to float. If you don't have those lines, it will want to go up and float just very close to the surface, but you keep it in place using these lines that they're all the time in tension. Yes, so that's why it's called positive buoyant, because if you don't have the lines in place, it will just go up. Okay, but I have the lines that are holding it in place, so there is all the time some force. It's not in equilibrium, but it's in equilibrium, but it will want to go up. Okay, we'll have some, and that creates something like, let's say here we have our platform, here we have the sea, and here we have these lines that are holding it in place. And it's a big issue to install this kind of structure. Okay, because to find the right amount of tension, how to tension the line, the relationship between ballast, so that's extremely challenging. Okay, it's a very complex marine operation. But the nice thing is that if, for example, you have some waves, okay, that are pushing the structure to the right, so now the structure is here, and now the cables, they look like that. You will have a force that is pulling the structure back into place. Okay, so that's really the advantage of this type of structure. Also, to the other side, you have the force on the line, and then that force has two components, vertical and horizontal. And if you go, you're displaced. If you go to the horizontal side, you will be brought back to place because of this force. Okay, that more or less clear? Let's see if I have one more picture. Okay, and you have also different types, different shapes, different flavors, but they are positive buoyant. Okay, and they look very much like a semi-sub. Okay, but they are not floating. They are held in place through these lines, and they have to be a very big tension. Okay, when something happened to these lines, they don't have the right tension, they get reattached, they broke, the ballast also is not proper, you're in big trouble. Okay, an example of that is the Hydrun, just here offshore Trondheim. We have one of these TLPs. Okay, any question? Now it's 3. Should we take a break, or do we take a break? Okay, 15 minutes. So now the big question, okay? You say, okay, fine to know how they look like, how they're classified, but how really do we choose these structures? How do we determine which one is the best for my field? And really, I'm not going to give you a magic answer, okay, but I'm going to give you what you should look to, and we are going to discuss some of these issues. So first, one of them is water depth. Okay, we're going to see right away. Another thing is artificial lift. No, another thing that goes before that is reservoir structure. And extent. Okay. Then another thing is characteristics, ocean, what they call it, ocean ocean conditions. Okay. And that has an effect also on the loads that I will experience. Okay, the ocean conditions, that means wind, waves, and current that I have. Then we have a soil, as I told you before, soil characteristics. Okay. Then we have if what kind of artificial lift. Okay. And this reservoir structure and the well artificial lift, they are related to dry versus subsea wells. Okay. And also we have storage, if we need to have storage, and storage is related to the ocean conditions. Okay, so everything is kind of interrelated. And then we have future development plans. Okay, if for example we know in the future we will have to drill more wells, if we will need to drill more wells to maintain plateau or maintain production. Another thing is the availability and also the time, when the delivery time. Okay, and the availability. And one more thing is the experience of the company with that particular type of structure. Okay, some companies, they say we don't want to know anything about that, we haven't worked ever, and we will never work, we don't like it. Okay, so that's experience of the company. Okay, so let's try to go, I'm not going to go one by one, but at least I want to make comments on the depth, on the ocean conditions, and how that affects the loads on the structure. Then on this issue that also involves this issue and this issue. Okay, these are like three that are interrelated. Very few comments on storage, and then the rest I will just make some comments. Okay, but mainly our calculation part is going to come here. Okay, you will have one exercise on ocean conditions. Okay, and how that affects the offshore structure. Okay, so first water depth. Okay, and of course you can already see jacket, we can make it only of certain length. Okay, if we want to go 3 kilometers, that's not physical. So for that, let's see at the chart that shows what are the maximum and minimum length or water depth of the offshore structures installed. Okay, just to see where we are. Okay, so you see, for example, that jacket and gravity-based structures, the highest or the longest is 413 meters, Bullwinkle. I think this is in the UK. No, that's in the Gulf. And then compliant tower, they try to expand a bit further the range of the jacket, but you go to 600. There is no compliant tower in the North Sea. Okay. Then we have, those are really the king or the they are the king of the kings of the low depth, okay. But then when we go to the high depth, really the kings of high depth is the Fpso, and you will see that Fpso is a synonym also of subsea wells, okay. But jacket you can have really, dry and some subsea, okay, to reach some part of the formation that you cannot reach from the platform. And then you have all of these guys in between that they really more or less there is some overlapping. You see tension leg platform from 148 to 1500 meter. That's in meter, okay. Spar also they are for high depth and semi-sub. Okay. So it's not clear, not really clear. You got from this figure that for very deep water heights we use Fpsos, and for very low, for very shallow waters we use jacket and gravity-based structure. But in between we really have some several options. Okay. So now let's go to the issue of dry versus subsea wells. Okay. And as I told you, dry is that we have the tree, the Christmas tree is in the platform, is in the offshore structure. It's on the offshore structure. And subsea, just the Christmas tree is in the seabed, okay? So when to choose one or the other? That depends, first on the reservoir structure. Okay, as I told you, if we have a very compact reservoir that is easy to reach from the same place, okay, then compact, okay, and not very spread, then in that case we tend to go for dry wellheads. Also dry wells, they have the limitation of maximum depth is 1700 meters, okay, and above that you have to use, usually you use subsea. I think that's the current record, is 1700 meters. And what did I say? So to have reservoir structure, it is very, it's, you can reach it from the same place, and really the only structures that that have small enough movement to allow to have dry trees, it's that have low movement, okay, because imagine that you have all of this, okay, the well goes all the way to the, let's say that we have a ship, okay, and then we say we drill the well, we have our Christmas tree here, okay, we have all of our wellhead casing, everything that goes up, okay, and here it goes all the way to the formation. But then if this one has significant movement up and down to the side, that's going to attempt to the integrity of the well, and probably in one part of the life is going to fail just because of extreme deformation, extreme movement. So really the only structures that have low movement that allow to have dry wells or dry wellheads, okay, shouldn't say wells but wellheads, is of course jacket. So that is in this bottom supported structure. Okay, where we have, if you remember, we have jacket, we have gravity-based structure, and we have also tower, okay, the compliant tower. And also from the other group, the floating group, we have just the TLP, because of this particular characteristic that when you try to move it to one side, it's going to go very quickly back. Okay, TLP and spar, because what I told you here, the movement, the heave movement that is up and down, how much the spar is moving, is more or less 3 meters. Okay, so we are not talking really that it doesn't move, it moves, but this 3 meters is enough so it won't cause any damage to the well. Okay, TLP, spar, and we have that's all. Okay, so if we want to have, let's say we want to have dry Christmas trees because we want to reach everything, and also another reason to have dry Christmas trees is that I need frequent well intervention is required. Okay, if you know that is you have problems that you, for example, might plug the formation, you might have some very corrosive that you will have to change or replace the tubing, or you need to change equipment in the well, you have to do sidetrack. In that case, if you need to perform well intervention, then you want to have really access in the top to the well, that you can make any change, you can access very quickly the well. Okay, that's another reason. So reservoir structure, if I want to perform frequent well intervention, and one particular example is if wells have ESP. Okay, electric, ESP stands for electric submersible pump. Okay, it's just a pump. If we see, now it's getting messy, let's make one more space. Okay, so if we make the drawing of our well, let's see, we have the casing, the tubing, the casing, we have our perforations, here we have our reservoir, and here we have all the rest. Okay, so we put exactly here, we put a pump that is going to help and give a pressure boost to the fluid. So here I might have a very low pressure, a very low bottom hole pressure, that if I leave it without the pump, it won't be able to reach to the surface. Okay, but when I get this pump, it's going to boost the pressure, and then I'm able to flow that particular rate. Okay, but the thing is that these pumps, they have a lifetime, okay, of between maybe 1 to 5 years. Okay, and 5 years really if you're lucky. We say really that between 1 and 2 years. So if you know already beforehand, I need to develop that particular field with pumps, or I need to do intervention, I need to change the tubing, I need to do sidetrack, I need to have access. So this really need to access the wellbore often. Then I prefer to have dry Christmas trees. Okay, like just in contrast, okay, subsea wells have an average intervention time of 5 years, okay, which is much sparse or much less frequent than when you have, for example, a pump, or when you want to make intervention. So that decision, you take it first is the reservoir is not very spread. Okay. Secondly, also another thing, what does it mean that the reservoir is spread? That, remember that the longer, let's make another discussion here. Okay, remember that, so let's say, what is the meaning of spread reservoir? Okay, or compact, or how do we call it? spread. The other name is yeah, kind of localized. Okay. When you want to reach a particular, let's say that here you have the particular area that you want to reach, and here you have your vessel. Okay. You have certain limitation on the total length of the total measured depth that you can reach. Okay. If you go far away, then you will have more friction on the and you because here remember you have some drilling machinery that is rotating this bit, okay, and it has a limited capacity. When you go longer and longer and longer, you have more and more friction, and you need more and more power to rotate it, okay, and it means also you need to have a bigger drilling package, okay. So that's what I'm saying, that is relatively close compared to what I can put on top of the offshore structure. Okay, what I can afford. I can put really just a huge drilling package, and I can, Yossi will reach 13 kilometers, for example. But that will be, for example, heavier. I need a bigger offshore structure, will cause more cost to the project. So that's usually, so it's within my limitations. Remember all the time that the spread or how I can reach the reservoir depends on my drilling package. This depends on the drilling package. Okay. So let's see, in the seabed, reservoir structure, so let's put here, try to make some order. I choose dry Christmas trees if depends, okay, on the drilling package. And so that really limits our choice. What do we have? If we feel that we need dry Christmas tree or dry wellhead, so then we are limited with the number of choices that we have. And there is a very big difference between the two. If I for jackets and GBS, okay, the wells are drilled just like onshore. Okay, just have my platform, for example, my jacket, okay, and I put my conductor, I put my BOP on top, and I start drilling, okay, just like if it was an onshore operation. Okay. Now when I drill for TLPs, okay, spars and compliant towers, the movement is significant. Okay, like I told you, in spars might be 3 meters that goes up and down, up and down. So I have to do something. I cannot transmit all of that load to the well. So what I do is I have a wellhead, in the seabed. All of you know what a wellhead is? Yes? And what is the function of the wellhead?
Yeah. To hold the Christmas tree.
Well, that's one of the functions, that is to support the Christmas tree, okay? But there is one more important function.
Hold the casings.
Okay, hold the casings, but also?
BOP.
No, yeah, but the BOP is only when drilling. To hold the casings, but to avoid that the pressure in one annular space will communicate with the pressure in the outer annular space. To seal, okay? So the function of the wellhead is support or support the casing. Okay. Really, the wellhead is to transfer load of the Christmas tree to the conductor, okay, to the soil. Okay. But then has one more thing, that is to seal between annular spaces of the casing. Okay. because I have, remember that I have my hole, then I put one casing, okay, and this casing, for example, initially, so let's make it, okay, this casing is very big in diameter, but it doesn't have the rating, it doesn't tolerate too much pressure, okay. Then I go and in another casing that I put inside, okay, this one, for example, will be in contact with the formation, so this one has to withstand, let's say, 200 bar or 300 bar of pressure, while this one can only withstand, let's say, 50 bar. So if by any chance the pressure that you have inside goes on this annular, this casing is subjected to that pressure, it's going to explode, okay, it's just going to don't resist. So the wellhead is blocking, is creating a seal between those two areas, okay. Yes. Okay, so in that case the wellhead, so you have, in that case when you have that much movement, so let's see that this is the seabed, okay, here you have your well, so most of the casing hangers are in the seabed, hangers. Are located in the seabed. Okay, so you leave there, it's like you leave part of the tree. Well, not really the tree, but you leave part of the wellhead. Okay, then you put a joint that will allow some flexibility, because remember, what is up here is going to move a bit to the side. Okay, so you put a joint that is called stress joint. Okay, and then you put a piece of pipe that is called a riser. So let me make it maybe a bit nicer. So you have a first wellhead, okay. So this is a wellhead, okay, but only has the casing hangers. Then you put a big joint. Let me put the joint a bit bigger. Okay. Then you put a riser, okay, a piece of pipe. And then on the, let's say that this is the deck, okay, this is the deck, you put here the rest, you put here the tubing hanger, okay, and you put here the Christmas tree, okay. But to have the option that if you are moving, so that's let me let's say that this is okay, and that's the deck, and we have the ocean someplace here, put it with blue, okay. So to make sure, and here we have some rollers, okay, something, this is not fixed to the platform, but it's able to go through, okay. But if it's going to move to the right or to the left, that's going to force it to move to the right or to the left, the riser, okay. So you have the tubing hanger, you have the Christmas tree, and then what you have is a system. It's getting messy, the drawing, okay. You have a system that holds the riser, okay, a riser tensioner. You have, that's one system, okay, that it's going to, if this structure is moving up and down 3 meters like the spar, okay, this tension system is able to keep all the time in the same vertical position while the other is moved, okay. So it's a motion compensator. That more or less clear? Yes or not? So first, the elements. You have one wellhead at the base where you have all the casing hangers. Then you have one joint, which is, I forgot to put it here, that's called stress joint. That's supposed to keep the seal, but that's supposed to allow some movement in this direction, okay. Then you go up and you have the tubing hanger at the top, the wellhead at the top, but they are not fixed. The riser, the tubing hanger, and the Christmas tree, they're not fixed to the platform. They just are going through the platform, okay. And if the platform is moving, they're all the time kept in the same place through a motion compensator. Okay, and then you ask, okay, how do we connect the production? We just used it looks like a Barnehage drawing, huh? I told you to do nice drawings, and I'm doing a mess here, but let's see. Okay, so you have here your structure. Okay, riser is this one, and deck. Okay, here people are standing and they can observe. So you have one hose that goes from this part, and then you have another pipe. Okay, then you have another. So this pipe is fixed with the platform. It will move together with the platform, but then the movement up and down is going to be compensated by the hose. This is all the time in the same place. This is moving up and down, and then the hose connecting them is going to move accordingly. Okay? Yeah? More or less? So now let me pull the nice picture. Okay. Yeah, that's another system. Let me just talk about this one first. Okay, and here we don't have the platform, so we don't have any other complexity, but here you have a subsea wellhead, okay, that is just part of it, just as the casing hanger. Then you have the stress joint, you have the riser going up, and there you see in the riser you have attached a load ring. That's where you're going to put this support mechanism, this pulley system that is going to all the time to keep it in tension. Remember, this you are supporting all the weight. The wellhead can weigh quite a few tons, okay, like 20 tons, 40 tons. So you have to support that weight, okay, but also at the same time you have to allow that the platform will move independently. So that's why you need this pulley system that is not shown here, but is here. Okay. Okay, some rollers, what I told you, to allow when the platform moves up and down, that it won't affect the riser, will be friction, okay? But it can move on this direction, so that's why I need the stress joint. Okay? So that's a much nicer drawing, okay? So here I have a pulley system, and here it's, for example, the platform, the deck, okay? And it's going up and down. And there is another system that is, this is typically used in spars, that you have some buoyancy cans that they are attached to the riser. Okay, so they keep it floating all the time. So you get this tension instead of using a pulley, you use just the air cans keeping it up all the time. And what you have to make sure is that there is free movement between the spar and the riser. Okay. Okay, what else? Okay, so if dry wells are used, usually the offshore structure has a drilling package. Okay, and that you can see right away that that it looks like this. Okay, you have a big drilling tower in the center, so that you can see right away if it's a platform. Okay, then they want to have really to be able to control and have intervention whenever as needed. Okay, what else I'm missing? Okay, that's not to say that you cannot have when you have when wells are subsea. Sometimes, and this is not often, the offshore structure has a drilling package. Okay, and that's, for example, in the case of Njord, that they have it's a semi-sub. Okay, so here I shouldn't have put a semi-sub, but this is yeah, spar. Okay, but you understand the okay. And you have here the drilling tower, but in that case, all the subsea wells, they are located exactly below the semi-sub. Okay, all the wellheads, they are located here. Okay, so they want to have it just in case they want to do intervention, subsea intervention in one of the wells. Okay. But it's not the common case. If you have usually semi-subs and Fpsos, they don't have drilling. They don't have a drilling package. Okay. Okay. Some things, other things that is important to note are dry well structures have limited number of well slots available. Okay, you have remember you have a bay where you have all of these slots, and really you want to use all of them. But if you have plans in the future, let's say depending on, also you don't have all the information on the reservoir. So let's say some years in production, after 2-3 years, you realize there is an area that is not really connected to the rest. Okay, that is, there is a fault, or there is something that a shale layer, something that is not connected. So you need to drill additional wells. So for dry well systems, you don't have usually that flexibility because the number of slots, they are really limited. Okay, so if you have some uncertainty about the formation, you think that you will need drilling, for example, infill drilling. Okay, that is usually drilling to maintain the production rates. Okay, then you try to, it's not very flexible. Okay, then another consideration is systems with subsea wells have to you have to perform flow assurance. Okay, you have all of these issues: wax, hydrates, scale, and so you have to take that into account if you are going to make the well subsea. Okay, in systems with subsea wells, production can start gradually. Okay, as soon as the offshore structure is in place. Okay, let's say you have some subsea wells, okay, that you're drilling, and there you have in place the Fpso, okay, with your separator, your facilities. So you can just go and tie in as you need. You connect that well to the Fpso, then you go and drill another one. You also connect it to the Fpso, drill another one. So you can have this kind of ramp up production, and you can start getting revenue relatively soon. Okay, when you have a jacket, for example, on any platform where you have the drilling package on top, really you have to drill all of the wells before startup. Okay, you cannot be doing drilling and production at the same time. Okay, so that's something that this gives you. If you say QO versus time, okay, that's going to, you're allowed to do something like this stepwise, but here really it's just a step and then down. Okay, so that gives you this is called a delayed cash flow. Go. And then here you get forward cash flow. Okay, you start recovering some money early on. Okay, that more or less clear. Dry wells at the end is an issue on the reservoir, how intervention, artificial lift, and also the size of the package that I need. Okay, might be that you just need a very big package and the offshore structure will be just too big. Okay, that's why I told you all of these issues are related that we mentioned before. Now there is one more thing, that is the storage, okay, of oil. And really the only structures that have storage are, and storage has to do with, remember that the oil is transported by tankers, okay? So you depend on a certain schedule of tankers to go back and forth from your field. But if you are in a location that you have, for example, rough sea conditions, that the tankers will be, for example, there is an alarm and they say 2 big waves, you cannot go to that place, then the only option is to shut down production, okay? And that's going to affect negatively your operations. So in those cases, you want to have some buffer that you can store production fluids for some time and don't stop production. And then when the tanker comes, you just transfer all of that directly to the tanker, okay? So structures that allow storage are Fpso, okay, and gravity-based structure. All the rest, they have really limited or they have very little storing capacity. Okay, so and this we are talking GBS, gravity-based structure, maybe in the range of 300,000 barrels of oil. But FPSOs really, they can go, I think the limit is 2.5 million barrels. Okay, so really they can store, no matter what's happening in the world, a catastrophe, the tankers, everything, they can still be producing for quite some time before needing to transfer to the tanker. Okay, and this is a very common option offshore West Africa, and yeah, and also if I need some storage, I want to put an FPSO nearby. Okay. Only one, maybe one. The only exception is the spar. So now you have to help me. How do you write Osta Hanstein? That correct? Yes. Looks fine. Yeah. Okay. So it's the only spar with storage capacity up to date. Okay. Well, up to date is not yet in production, but is the first one designed with storage capacity, 150,000 standard barrels. Okay, which is not much, but this field is a gas condensate field, produces some condensate, and the gas is there is a pipe. I'm not sure if you have seen where the is how do you call this? See, no, we make okay, very professional map of Norway, someplace here, okay, and then they're going to hook up with the gas transportation line that goes to Kosto, to Kolsnes, but they are producing also some liquid, and this liquid they cannot send it through the main gas pipeline, okay, because it's not allowed. So if they have too much liquid and they depend all the time on a tanker that is going to come back and forth, that's going to stop probably, and that's a very harsh environment. Okay, it has a lot of high waves, big waves, so it might be affected by this issue. So what they wanted to have some buffer where they can store some liquid and not stop gas production. Okay. And let's say here to clarify Norway, and that's yes. Any question so far? No? So now we go to the last part that I want to discuss, that is offshore. So it's marine loads on the offshore structure. Let's see if I have something else. Okay. But I think it's better if we leave that for next week. Okay? What do you think? Yeah? Because that's a part on calculation. So, but that's another very important thing, that we have to consider where are we going to place this offshore structure. Okay? You will see that they have some particular response. For example, floating structures, they behave like a boat. Okay, they have movement in this direction, in this direction, in this direction, in all of these directions. Okay, then platforms, they have movement, deflection in this direction, and they are, because of these characteristics, they are susceptible to certain particular loads. Okay, some characteristics of the loads. So we have first to characterize the loads, which are waves and wind and current. And I'm going to tell you briefly how do we characterize them. And then we have to characterize the response, how the structure is going to respond to these loads. Okay? And based on that, there is a range. You will see that these structures behave better than others. Okay? So let's close the session. So what we have seen today, a very general introduction to offshore structures. You saw the main functionality that the offshore structure has to have. Okay, doesn't have all of that, but some of it. We have bottom supported, and then we have floating structures. Okay, and then we saw some things that affect the decision. Okay, most important, the dry wellheads, dry Christmas trees versus wet Christmas trees. Okay, subsea wells. And yeah. And then we saw, what else? The storage. And next class we're going to see the marine part, the offshore part. Okay? Any question before we close? No? Okay. Yeah. Just